So, let's talk about homework number 1, which is due on Friday at midnight. Okay? Just a few things. Number 8, pore pressure gradient. You know how to do that. Number B, vertical straight gradient. You know how to do that. For the depth at location A, also we talked about that. We know how to write tensors now as matrices. And for this case, remember that the values I want are total stresses. If you did effective stress too, that's fine. And we talked about what is normal strike, slip, and reverse regimes. You will see that they are now all on the same regime at all depths. About the 3D Moore circle, we talked about that too. We didn't say how to plot that in Matlab or Python, but I'll leave that so you can search on your own. But as far as I know, for example in Matlab, there is no direct function to plot a circle. So instead what you do is you make a list of R cosine, R sine values, and that's going to give you a circle.
What about Matplotlib for Python?
You can use that too. I'm not sure if you can plot circles with that.
Yeah, I don't know.
But if that's not available, just calculate several points along a circle and then just plot that. Okay?
So for 3D Moore circle, it's just like you have 3 principal straight, right? That's
You have 3 circles.
right, yeah.
1, 2,
3.
you plotted 3 circles.
That's it. Okay.
That's it. Okay? We talked about what is P and what is Q. This should be P prime. We talked about Q. We talked about I1 and J2. So you know what it is, and you can calculate it too. Remember, always with the general formulas for 3 dimensions. Yes?
So, I guess I'm an old school guy, so I draw these more circles on the paper.
Yeah.
Is that okay also?
That's okay. That's okay. But just take a picture of that, convert it to PDF, and add it to whatever you have. But you're going to have to do this for the next assignment. You're going to have to put points inside here.
Okay.
So I recommend that you start coding that because you're going to need it. And also the next assignment, probably this one could be solved in Excel. The next one is going to be very tough to do with Excel. So you need something else. You need either MATLAB or Python. Okay? And this one is just a conceptual question. Remember, hydraulic fracture is going to open up pushing against minimum principal stress. All right, so you should be able to do number 1, and number 2, you should be able to do it as well. Remember that I gave you an example. In my notes there is an example of how to do that. Probably the only thing which is a little bit tricky here is to combine the deviation survey file with the logging file. But I suggest, if you're struggling with that, I suggest that you do the following. Assume measure depth is true vertical depth, and do all your computations with that. And when you get it right after you're sure you get it right, then try to correct for the true vertical depth. If I remember well, in this is an almost vertical well. So the difference between measured depth and true vertical depth at the end of the log is something like 50 feet, like in several thousands. So that's nothing, okay? But I like that you do the correction anyways, because that's something that you may need in the future and in a general case. But this is just a problem of numerical integration. If you have any questions, then you can stop by my office. I put now office hours from 6 to 7 on Wednesday, so that will be today. And also after class, anytime, if you bring your computer and you want to take something together, you're welcome to do that. And also, there is I added the information. I don't remember if I showed this to you last time, but I added the information of the TA, whose name is Georgine, and he's going to be also able to start. So if you go here, you'll find Georgine's email address. I think he didn't set some official TA hours, but you can send an email and you can talk to him. Okay? All right. So that's for the project number 1. And today I'd like to start talking more in detail about project number 2. The objective is that given the state of stress at a certain location, we want to calculate what are the normal stress and the shear stress on a particular plane. And such plane could be, for example, a fracture. And we want to know that because we would like to know if some of those planes, they have a relatively large shear stress compared to the normal stress, or if they have a huge normal stress that maybe could be closing the fractures. For example, this is very important for microseismicity. Why? Because the fractures that have the highest shear to normal stress are going to be the ones that are going to be more likely to be reactivated and more likely to induce or to produce induced seismicity. So this computation is very important. And what we're going to do is we're going to look at the equations that we need in order to calculate this shear stress and normal stress. We saw that in 2 dimensions is relatively easy, and the equations are just 2 lines. This is the value of sigma n. This is the value of tau. And that's it. That's in 2 dimensions. In 3 dimensions, it's going to be a little bit more complicated. But not impossible, and it's not difficult either. It just requires a little bit more of mathematical operations. So in order to get to the solution in 3 dimensions, we saw that it's going to be the result of multiplying a matrix times a vector, in which the vector n tells you the orientation of the plane. So this stress is going to come from the in situ stress. And this vector n is going to come from a particular fracture or a particular plane. The objective in this project is going to be that we calculate all those values of tau and sigma n for a set of fractures. All right, so we have the equation, but however we need something else. And we need that something else. It's a common coordinate system in which the in situ stress and the fracture can be multiplied. You cannot do this multiplication in 2 separate coordinate systems. So we have to agree on a coordinate system. So we write the stress tensor in that coordinate system, and we write that vector n in that coordinate system, and then we can make the multiplication. And then that coordinate system is going to be the coordinate system NED, where N is the first element, E is the second element, and D is the third element, and N is the north, E is the east, and D is the direction going down. All right, so let's go first with the in situ stresses. There is no reason why the in situ stress or the principal stresses might be aligned with the north, the east, or even the vertical direction. In general, I'm going to have principal stresses which are at an angle which is different from these directions. And let's say in this example that I have, let me check the axis. Yeah, I could do this. I could say this is sigma 1, this is sigma 2, and this is sigma 3, where sigma 1, sigma 2, and sigma 3 are the principal stresses. Let me change that quickly to something that, so I don't do it twice. If I find my eraser. I forgot. No, wait. Okay, let me change this to S. So this is going to be the principal stress, and this is the same as saying S1, S2, and S3. And the principal directions are not aligned with the directions of the coordinate system. In the direction of the principal direction, which in this case is going to be the direction of these principal stresses, 1, 2, and 3, these are going to be the principal directions. I can write the stress tensor, which I'm going to call SP, and the P comes from principal, which is a stress tensor written in the coordinate system of the principal directions as sigma 1, with sigma 1 larger than sigma 2, or I like using sigmas instead of s's, but for this example, I need to do it with s. Let me continue then with s. So, in the coordinate system of the principal directions, the tensor simplifies to this with non-zero elements in the diagonal and 0 elements in the diagonal, in the off-diagonal terms. And that's it. That's how you write. Okay, but we said that we need to write this stress tensor in order to make the multiplication in this coordinate system, which is the geographical coordinate system. So I have to do something here. When I write this tensor in the geographical coordinate system, then now the elements are not going to be 0 in the off diagonal. And I'm going to call that element the vector, the tensor SG. And in general, as I said before, I'm going to have numbers here that are not going to be equal to 0 necessarily. Okay, so the question is now, how do I get this matrix? Well, this matrix is going to be the result of the matrix multiplication of a transformation matrix going from the principal to the geographical coordinate system transpose times the tensor in the principal direction coordinate system times this matrix again. And you may ask, what is this transformation matrix? Okay, this transformation matrix is a function of the projection of each of these directions in there. And each of these directions, we're going to relate it by angles that we're going to call alpha, beta, and gamma. And with those angles I'm going to show in a minute, they're kind of difficult to draw. I'm going to be able to calculate this matrix RPG. And this is a huge matrix. So I'm not going to write it here, but I'm going to tell you where you can find it.
Oh, can you repeat what the transformation matrix is again?
The transformation matrix, it's a matrix that it tells you the projection of, for example, this vector onto N, E, and D. That's the first row. The second row is the projection of vector 2 on N, E, D. And the third one is the projection of vector 3 on N, E, D. And it just tells you the direction of the principal directions in the coordinate system, in the geographical coordinate system. And in order to make that easier, instead of doing just dot products all the time, we're going to define three angles, alpha, beta, and gamma, that will allow you to calculate this matrix